Hello, everyone. Thank you very much. Come from our workshop, and this is our second workshop for the cooperative multi-agents, the cognitive modeling. So I will very glad to thanks the Professor Lee and the other Professor Altens and help us to make this come true. And yeah, since this workshop's main purpose is to consider maybe currently the robotics and IoT and edge computing is increases the development in the future. We are inevitable let this the artificial social system integrate in the human society. So a lot of the issue might be come up like the people just worry about whether or not this kind of the intelligent agent will replace stolen our work and even become a certain kind of a threat to the human species. But from another perspective, some of the science fiction movie, maybe like the Star Trek, we have very like the strong AI agent like Data, also have a negative the agent like the Terminator. But in the future, what kind of the the strong AI agent we will build is really depending on ourselves. So this workshop we might be from the cognitive science the perspective to discover whether or not we can find a suitable way to develop a reasonable direction or architectures to build a friendly AI to integrate in our human society and support entire human sustainable development. So that is the key purpose for our workshop, and I hope that you guys can do some brainstorm and give us also some good suggestion. And I also invite one of our organizer.
Yeah, thank you, Professor Yang. So indeed, it's a pleasure to have you here. And I think we have an exciting program today. So with a series of invited speakers that will talk and cover the topics that Professor Yang introduced. And at the end of the workshop, we will have also a panel discussion. So I think that during that time, hopefully we can sort of wrap up, right? So some of these ideas and continue, right? So even beyond, I guess this workshop. I think that indeed, the time is exciting. Also, with the development of foundation models and LLMs, and also in the application in robotics and multi-agent systems. So it's going to be really exciting. I think that hopefully everyone will have the chance, right? So really to join and participate in this discussion. I think with that, probably we can start with the first invited speaker, I guess.
Yeah. So our first speaker is Peter Stone. He's come from the United States Austin, and is very famous in the artificial intelligence area and robotics area, especially in the multi-agent, multi-robot system. And he might be very I believe that is from my perspective might be the very first guy to study in the also very successful in multi-agent and multi-robot studies. And yeah, it is our honor to invite him to come here give us the talk. Yeah, thank you very much.
Thank you very much for the kind introduction. although I have to say that I was definitely not the first to be doing multi-agent systems or multi-robot systems. There was a very rich community that started before I entered it. So, and you'll be hearing from some of the speakers before that. So, who came before me and whose work I've built on over the years. Thank you also very much to the organizers for inviting me. I'm sad that I actually I've been here for the week, and I have a commitment back in Austin tonight, so I'm going to need to leave right after my talk, and that makes me sad because I see such a fantastic lineup of speakers throughout the day, and I really wish I could be here for the whole time. What I'm going to talk about today is an area that I've been fascinated by over the last 15 years or so, which is what I call ad hoc teamwork. It was introduced as a challenge problem to the community about 15 years ago, actually here at a AAAI conference. And you know, it struck me that sort of creating this workshop is a pretty good example. So our organizers have done a great job at pre-coordinating us and making a schedule and everything. And yet I showed up here without having uploaded my slides, and trusting that without having followed all of that pre-coordination, we could on the fly still collaborate on being able to get my talk presented here. And this is something that people are able to do, but that we haven't really focused much on having agents do this collaboration without pre-coordination. So I'm going to spend, I'll tell you a little bit more about that. But first, I just want to take a brief introduction of myself. I know many of you here, but not all of you know where I'm coming from. I am at UT Austin, University of Texas at Austin. Really exciting times there. We have now two AI institutes, NSF. We have one of the first ones, the Institute of Foundations of Machine Learning, and now also one on cosmic AI, or AI for astronomy. I've been a founding member of a really exciting sort of bridging barriers or grand challenge program at UT on which we call good systems, which is studying the societal implications of artificial intelligence, and includes a very cross-disciplinary mix of people that was inspired in many ways by the 100-year study on AI that I've been a leader of. And right now I am director of Texas Robotics. We have a beautiful new space in what used to be a gymnasium that's now, this was before we filled it with robots, but now full of robots. We're hosting the conference on robot learning in 2026, and I hope all of you will be able to come and see the old Anna Hiss gym that's now filled with robots, but also a lot of innovative AI education happening. I spoke at the AAAI workshop yesterday. And we now have in robotics more than 17 core faculty who publish in the top robotics conferences. Where I come from personally is my research question has always been, to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? So for the purpose of this workshop, the teammates is key. That's the cooperative multi-agent systems. I've tended to publish in these sort of sub-areas of artificial intelligence, and I'll focus today especially on the multi-agent systems and to some extent learning. When I give a one-slide introduction to my lab, there is a lot of sort of algorithmic and theoretical work that I do, but it's easiest to see sort of more the problem-driven research or the use cases that have inspired me over the years. I'm not going to show videos of them here because of limited time, but I've done a lot inspired by robot soccer, where we have the goal of the year 2050 to create a team of humanoid robots that can beat the best World Cup champion on a real soccer field. General purpose service robots that can be in our midst, moving around, doing things for us, manipulation, interaction. We focus on that, and like many, I've been also very inspired by autonomous driving as a cooperative multi-agent system. And most recently with my team at Sony AI, we've focused on creating a superhuman AI agent for the game Gran Turismo, a very high fidelity racing simulator. It was sort of in this series of AI systems that can beat the best human at something, right? Be it chess or Go or poker or Jeopardy. This was the first time it was at a real-time control task. If you're not familiar with it, this is what it looks like. This is a sort of top and down or up and down view of a expert race car driver, Ken Chan, driving a real car in the real world on a real track down below, and the same car on the same track in the simulator up above, and he finishes a lap within 1/10 of a second of the time. And you can see that it's sort of very high fidelity modeling. And you can see like a whole 1 hour talk on my website on how we did this. It was an end-to-end deep reinforcement learning approach, and when we beat the best people at this, it was landed on the cover of Nature. It's now out in the video game, and there's hundreds of thousands of people interacting with this reinforcement learning agent, which I think is one of the largest commercial successes or deployments of a reinforcement learning agent. But today on this, in line with the theme of this workshop, I'm going to be talking about ad hoc teamwork. And in particular, I'm going to focus in somewhat deeply on two recent papers. One on minimum coverage sets for training ad hoc teamwork agents that was published at AAAI last year. And then one on a recent NeurIPS paper on a generalization of ad hoc teamwork, or the original formulation that we call N-agent ad hoc teamwork. So diving right in, I'll talk about half the time on each of these. Minimum coverage sets for training robust ad hoc teamwork agents. This is led by a postdoc in my lab, Arash Rahman, and a PhD student, Jashun Kui. In the context of this work, I'll give a little bit more detailed introduction of what we mean by ad hoc teamwork. And if you take nothing more from my talk, if you're not previously familiar with ad hoc teamwork, I hope what you get is what this problem is, why it's interesting, what some of the challenges are, because I think there's been a nice vibrant community focusing on it, but I think there's still tons of open challenges. So the idea is that when we started this, the business as usual for multi-agent systems was to study pre-coordinated teamwork, where you're trying to where an expert would provide agents with coordination mechanisms such as conventions or role assignment mechanisms or communication protocols. Or that agents would learn and establish these conventions by interacting with each other for an extensive period of time. In collaboration with Rich Sutton, I had a paper at ICML 2001, where we had robot soccer agents learning together to cooperate as a team, but they got to practice tons and tons of time together as a team. And so that was is business as usual. The team is there from the beginning. But for that, there can be coordination issues, can be a problem. They all collaborate well if they follow the same mechanism or if they train together. But if some agents don't do that, things can go awry. And so the idea of ad hoc teamwork is, again, that people are able to coordinate without this pre-collaboration. I'm a soccer player. I can go to a foreign country to see people that I've never seen before. I don't even speak the language with them, but I can jump on a soccer field and we can play soccer together immediately without training. Or if you have an experience ever, I hope this doesn't happen to you, but you're walking down the street and there's an accident, a crash of two cars. A bunch of total strangers will spring into action, with one searching for victims, one calling 911, one redirecting traffic. This is collaboration without pre-coordination. So the question is, how can we do this for robots? How can we equip the robots or software agents with this goal, with this ability? And so the original formulation is that we control a single agent, and we want to maximize the team returns, and with the idea that the teammates use some unknown policies and possibly unknown coordination mechanisms, and we can't establish these prior coordination mechanisms. And so So an example that I'll use throughout this portion of the talk is, imagine you had, AHT is now an abbreviation for ad hoc teamwork. So a good ad hoc teamwork agent would have in its arsenal of possible strategies, a good coordination mechanism for any teammate it could be faced with. So assume that you're in this matching rock, paper, scissors. So not where we're trying to beat each other, because that's adversarial. We're in a teamwork setting. So let's assume that we're both happy if we shoot paper at the same time, or scissors, or rock, right? So it's a matching. We get a +1 reward for matching and a -1 for mismatched, right? So this makes it a team problem. A good ad hoc teamwork agent would be able to emulate or play the role of a best response agent to any possible teammate, right? And if you know the game, you can quickly intuit that if you're playing with a teammate that has most of the time does rock, then you want to all of the time do rock. That will maximize your team rewards. And similarly, if it most of the time does scissors, you want to all of the time do scissors. But the key is you need to have in your arsenal the ability to play any of these best responses. And so in this, the sort of high level motivation for this first piece of work is that we want to try to find the class of teammate policies that induce the full set of possible best responses, so that if we train with them, we'll learn an ad hoc teamwork agent that's prepared for any future teammate it might come across. So hopefully that makes sense, is that you want to find a diverse set of teammates to train with, so that when you are sort of plop down in the ad hoc teamwork setting, you're ready for any of them. And so the question that's addressed in this paper is, how do you identify such a diverse set of teammates? And so one way of thinking of this at this formulation of the ad hoc teamwork problem is that it's easily solved if we know the set of teammates policies that will be encountered. So we call pi eval the policy space of the agents that you're going to be evaluated with, the ones that you haven't been able to pre-coordinate with. And there's a set of all possible policies. And so in this diagram, if you think of these red agents as being this sort of right oval as being the ad hoc teamwork agent, and this is all of the set of teammates that it might interact with, there's some subset that it's going to be evaluated with. But and so a good ad hoc teamwork agent, if it has in its arsenal the ability to play the best response to any of those, and it can recognize who it's coordinating with at this moment, it's going to be perfect. Now, what's the challenge? Right. So first it might have a teammate classifier when it finds its teammate, say which type is it, and then it would sort of use its best response. The challenge is that you're going to find some training agents that are not going to be the same as your evaluation agents. You don't know ahead of time who you're going to have to collaborate with, and so the evaluation set is unknown a priori, and there's in general there could be infinitely many policies, so you can't train a best response to each of them. So we're going to have to try to select a few policies for training, and hope that it, as well as possible, prepares us for the evaluation agents, the ones that we're going to find in the end. And so these are not necessarily going to be the best response policies to the evaluation ones. And so this paper was a response to there's some past work on a concept called maximizing adversarial diversity. I'm not going to go into the full details of this, but sort of state of the art methods from the previous years. We're trying to maximize a concept which can at a high level be described as coming up with a set of training agents such that if you compute their best response, you get the best response does really well against the training agents, but these best response agents do poorly when paired with the other training agents, right? So you want a diversity of training agents so that the same best response policy isn't good for all of them. You need to learn a diverse set of best responses against your training policy. In other words, to make you prepared for a wide variety of possible evaluation agents. And so the formulation, really the commonality of all of these previous methods, has been to try to formulate a methodology for coming up with training agents that have, and best response agent pairs that have high self-play returns and low cross-play returns. But it turns out, and this is sort of the key insight of this paper, and the details are there in the paper, the AAAI paper from last year, is that maximizing this adversarial diversity concept doesn't actually lead to discovering all best possible, as diverse a set of best response policies as you might want. The generated teammate policies could actually still sort of double up on each other, right? They don't get spread out as much as you would like. Because some of them sort of, you end up with best response policies that do end up being good for multiple of the training agents. The technical details of this are a little bit too involved to get in the time that I have here. But again, it's all laid out in the paper. And there's a really nice sort of game theoretic example that establishes this. So so in this paper, we introduced a method that we call Lagrangian best response diversity that corrects this shortcoming. The idea is that it's based on a concept of minimum coverage sets. And so what's a coverage set? It's a set of best responses that that covers all of the, that is a best response to all possible teammate policies. And that if you remove one element of it, it's no longer has a best response to all possible teammate policies. So, a coverage set could have more than the minimum ones. You could have lots of different policies, but a minimal one is such that every one of those policies, those best response policies, is necessary. And so, if this is sort of a depiction of that rock, paper, scissors space, it's sort of a you can say what's your probability of picking rock, papers, or paper or scissors. The middle point being equal probable among all of them, and then the corners being one of those. The idea is that you want to pick a training agent that represents each of those regions, because this whole blue region all has the same best response, this whole red region has the same best response, and this yellow region has the same best response. So you want to try to identify one agent from each of these regions to be in your training set, so that you learn an ad hoc teamwork agent that covers this minimum coverage set. And then this is what I just said. You want to be able to sample one from each of these clusters. Again, I'm not going to walk through the full sort of linear program, but it's basically solving a constrained objective, where we have constraints that are trying to find as many different best response and agent policies as possible. And we want to optimize an objective that generates one teammate policy for each of the generate best responses, so they don't double up on each other. And this is sort of it's a carefully formulated linear program that allows us to do this. And then we are in the paper, we evaluate this in a few settings, in some matrix games, cooperative reaching, level-based foraging, and find that compared to the alternatives, we're able to find a and the way we evaluate this is that we generate, using this teammate generation method, a set of training agents. We then train an ad hoc teamwork agent against those, and then we compare the returns against some held out teammate policies, like exactly that ad hoc teamwork setting, and see how well they do. And our method, which is called LBR-div, is able to in all of the cases except one, do significantly better than all of the alternatives. So the summary of this sort of half of the talk, I know it's at a high level of abstraction, so it's, you see this as a sort of an advertisement for the paper, but the important concepts here are the concepts of a coverage set and minimum coverage sets for training partners for an ad hoc teamwork agent, and a teammate policy generation method that gets state-of-the-art results for teammate generation. And so the paper's here. So with that, I'll just, for the second half of the talk. So if I know that went a little quickly, or you lost some of the train, that's fine. Now is a good time to snap back in, because I'm going to change gears entirely to a different paper, still within the ad hoc teamwork setting, but now a generalization of ad hoc teamwork that was introduced quite recently at NeurIPS. And this is joint work again with Arash Rahman, the same postdoc from the previous paper. It's the first author is a PhD student in my lab, Caroline Wang, and it's also joint work with Ishan Durikar and Elad Liebman. I have pictures of all of them on the last slide. So again, same motivation. We're in the ad hoc teamwork setting where there's multiple agents having to cooperate. But the insight in this paper is that ad hoc teamwork is sort of at an extreme of a spectrum, where the other extreme is full cooperation, where that I sort of motivated, where the team trains all together, or there's sort of pre-coordination methods. And so here's a depiction of that sort of cooperative multi-agent reinforcement learning setting, where all the agents train together. And the depiction of ad hoc teamwork and sort of the very related concept of zero-shot coordination. It's actually there's a subtle difference between them that's quite important. So I'm talking about ad hoc teamwork here, but both of them share the setting where, as I've motivated, you train a single agent to cooperate with a bunch of unknown agents, and the generalization in this paper is sort of to turn that into a bit of a spectrum where you might control a subteam. right? So this would be the motivating setting here would be maybe there's a search and rescue mission, and and the U.S. brings some drones to go help try to search for the victims, and some allies, maybe from New Zealand or Australia or whatever, also bring some drones, and each of them are haven't been pre-coordinated. They each worked well as a sub-team, but they have to now on the fly work together and figure out who should be searching for the victims and who should be bringing supplies and things like that. We don't want to reprogram them. But we want them to be able to immediately work together. And so now it's like sub-teams that are controlled, and then a bunch of uncontrolled agents. And so the problem statement, the formal sort of problem statement of ad hoc teamwork, I could have introduced this before the previous section, but it's to create an autonomous agent that's able to efficiently and robustly collaborate with previously unknown teammates on tasks to which they are all individually capable of contributing as team members. And the generalization here is just to add one word. It's to create a set of autonomous agents that are able to do this. So the formalism in the paper is as a decentralized, partially observable Markov decision process, where we have a team size, some joint state space, action space, observation function. These are all sort of the normal components of a DECPOM-DP. But then we add 3 components that are shown here. That now there's a set of controlled teammates that are parameterized by theta, and theta is basically the function that determines their policy. So theta is what we're going to try to learn. How do these controlled agents behave? And then there's some set of agents that are uncontrolled, and so that comes from the variable u. And then there's a function we've introduced, a team sampling procedure that basically first samples how many controlled agents are there going to be and how many uncontrolled agents are there going to be, and then picks a team from the controlled agents and uncontrolled agents to meet that to meet those numbers. And so you need to come up with a theta that will lead to a good control no matter how your team is sampled by this function x. And then so that's what you're maximizing, the theta that leads to the control when the team is sampled according to this sampling procedure. And so the challenges here are we want to coordinate with non-controlled and potentially unknown teammates, and it's also that we have to cope with an unknown number of controlled teammates. So the paper starts with a theoretical analysis, because you might say, well, why do we even need to treat this as a separate problem? Why can't we just have each of the controlled agents pretend that it's an individual and just do standard ad hoc teamwork? And so we started with a theoretical example in a toy domain that shows that there are cases where it is actually beneficial for these set of controlled teammates to work together rather than to each work individually. And so the controlled agents can benefit by behaving differently because they know that they're a subteam. That might seem obvious, but we wanted to make sure that was the case. So there's sort of a toy domain analysis of that as an existence proof in the paper. But then the main contribution is the first algorithm towards solving this problem that we call policy optimization with agent modeling, or POEM. And the key ideas are that there's a teammate modeling function, and then a reinforcement learning function that uses parameter sharing, and then a critic with data that's trained from both of them. So on the next 3 slides, I'll expand on each of these 3 bullets and sort of break down this overall system diagram. So this is just the overview slide. So first of all, there's a component, which is sort of this upper left-hand part of the diagram, where there's teammate modeling, where there's first of all, a latent representation trained using an encoder-decoder architecture, where the controlled agents each take in a history of all of the past observations and actions during this episode, and try to use that to predict the next observations and actions of all of your teammates. So the idea is if you see how your teammates are currently behaving, you want to have a latent representation that's sufficient to be able to predict what they're going to do next. And that sort of incentivizes a representation that divides them into 2 different types. Right, so if you're in that soccer setting, you might have an agent that tends to be very offensive, or one that tends to be defensive, or a ball hog, or a good passer, or something. And it's important to know what type they are to be able to map what they previously did to what you predict what they're going to do in the future. And so this is there's sort of a latent representation that's then used to train as the input to both an actor and a critic in a standard actor-critic kind of reinforcement learning setting. And so the policy network is the actor, the value network is the critic, and then we use, in this case, independent PPO with parameter sharing. So that means that each of the agents is training from its own observations and actions, given its sort of observations of what all of the current controlled and uncontrolled agents are doing. And then they each update the same neural network so that there's that all the controlled agents are going to use the same policy, but conditioned on their own private observations and history, of the history. And then finally, there's a training procedure where during training, we have information from both the controlled agents and the uncontrolled agents. And so that goes to learn both an actor and a critic, a value function and a policy. But the uncontrolled agents are, it's sort of privileged information, because at deployment time, you're not going to get the observations of the uncontrolled agents. They're sort of the ones that are not in your purview. And so the policy is learned just from the information of the controlled agents. And so at deployment time, you don't need the critic anymore. You just deploy the policy. And so it's sort of one of these settings where you have privileged information at training time. And that's consistent with the theory of ad hoc teamwork, or the problem statement, that you can practice all you want with, before the deployment, but then when you're deployed, you have to work with uncontrolled agents you've never seen before. And so this gives this overall diagram of the agent modeling network, the team policy training with the privileged information from the uncontrolled agents, and then when you deploy, you just use the policy network. So then in the paper, there's a bunch of experiments in StarCraft and in some more toy domains like predator-prey. We train uncontrolled teammates using a bunch of different multi-agent learning algorithms, as shown here, where there's train sets and test sets, so that the test sets you don't have any exposure to before evaluation, and we compare against some sort of ablations, and a standard independent PPO agent that doesn't do any agent modeling, one that's trained for just single agent control that doesn't recognize that you're controlling a whole subteam, and then a naive multi-agent reinforcement learning setting that's trained just in self-play. And the results in the paper show that that POEM is, first of all, not the red stars show how well you would do if you tested against the same agents you trained against. So we don't expect to do that well. But then when we take the out of distribution agents, that's really the ad hoc coordination, we find that POEM is doing better than the best competitor significantly, no matter which algorithm the teammates were trained with. We study the generalization to unseen agents in StarCraft. We also have some results showing that there are coordination conventions that are learned if they're trained together, and that if you change the agents from the training agents, from matched versus mismatched seeds during self-play, there's a drop in performance, meaning that there are conventions that are learned when agents are trained together, and we also show some sample efficiency. I'm running out of time, so I'm just going to point to the paper for the full results. But there's a big set of ablation experiments that show that the effectiveness of sort of a necessity of all three components of the method. So again, these are the co-authors. Caroline's the first author, and it's with Arash, Ishan, Elad, and myself. The full paper was in NeurIPS. And with that, I'll just remind you that I've focused in here on two recent advances in ad hoc teamwork. One on minimum coverage sets for training ad hoc teamwork agents, and then this generalization to n-agent ad hoc teamwork, and the POEM algorithm. We've actually we're now in work in progress extending a competitor algorithm based on a multi-agent transformer architecture that's also for this n-agent ad hoc teamwork problem. So that's some ongoing and future work. But with that, thank you for your attention, and I'll be happy to take any questions. Thank you.
I have a few minutes a couple of minutes for questions. So if you want, you're welcome to come to the microphone, I guess, and ask a question.
Hi, Professor. Thanks for the nice talk. From the ad hoc teamwork, I see that there could be two cases. One is that all these agents, although they don't know each other a priori, but they are either fully cooperative or fully adversarial. That's two extreme cases, right? I'm thinking maybe in the real world, in general, people are cooperative. The agents are cooperative, but in some of these agents may have some budget to act adversarially. Is it possible that we consider also this kind of ad hoc team cooperation? Just consider there are some of these agents are budgetary adversarial, but not overall adversarial.
Yeah, so that's a great question. So first of all, if they're really adversarial, then I wouldn't call it teamwork anymore. So one of the, in the original formulation of the problem, we assumed that they really shared the exact same utility function. And what that means is that it's possible that your teammates are incompetent, but they'll never be out to get you. So you don't have to, unlike adversarial settings, you don't have to protect against the worst case and sort of shore up any vulnerabilities. But we have been looking at and others have been looking also at generalizations where it's not exactly the same utility function, that there's that they're possibly like in the soccer setting, sometimes, one agent has a contract such that they get more if they score more goals. They still want the team to win, but they have some individual incentive. Or, in the search and rescue setting, maybe the American troops want to, have a higher premium on saving the American victims or something like that, and same for the other countries. So in that case, many of the same kinds of methods apply, and we've actually extended this LBR-div algorithm to that setting. But I wouldn't go as far as going all the way to adversarial, because then I think it's a completely separate problem, because you have to be then protecting against the worst case. Then you have to be doing like minimax kinds of reasoning, and that I think is no longer a teamwork setting.
I see. It's more like in a basketball team, everyone wants to win, but everyone themselves also want to be the MVP, right?
That's right. Right. So that generalization we admit for. That's a good question.
Thanks.
You have a question?
So if you look at a high quality soccer team, right, there's of course all the skills of the individual players that have been honed over years. But for a particular game, right, the coach has looked at film footage and stuff and has some sort of strategic plan for the whole thing. And they've also practiced particular plays.
Yep.
Right. And so I'm curious how you mix this kind of thing. Right. And even during the game, right, the coach may be changing the strategy.
Yeah.
And injecting them.
So I think of that as sort of what we're responding to as that's sort of the business as usual for multi-agent systems. That the team gets to practice together, has like sort of they know each other well. It could be the soccer team, or it could be the search and rescue team that have all worked together on a bunch of drills. Then I think that allows for these plays that they've practiced, and the coach to just say one word that'll allow say change strategies. That's what's not available in the ad hoc teamwork setting. That's what you can't do if you have to collaborate without this pre-coordination. We're in the pickup setting where where these maybe professional soccer players are playing together, but it's their all-star game, right? And they don't have the ability to have practiced all their set plays before, or the strategy language. They have to sort of figure this out on the fly. And so I think what you're describing is more what's been studied but much more broadly within multi-agent systems, is how do you come up with those conventions? How do you and there even in RoboCup there was a coach competition where there was a setting where the coach imparted this strategic information, and you needed the players to be able to respond to it. But here, that's we're in the setting where that advantage is not available to us, and we have to nonetheless figure out how to work as a team. So, well, yeah. So one of the lines of research in ad hoc teamwork has been, what if there is a shared coordination language, right? So we could even just go to the level of natural language, right? If I'm going to play a pickup soccer game and I go to a foreign country, the first thing I might determine is whether the other people speak English. And if they do, then I'll say, how about I play defense, you play offense, that kind of thing. And then we have this language. So that's moving towards what you're saying. If they don't speak, if they don't speak the same language, then we have to just do it by observation of each other. And so there has been work in ad hoc teamwork where the first thing an ad hoc teamwork agent does is say is probe whether its teammates share a protocol or a language or a set of strategies. And then if they do, we'll leverage that. And so that would be sort of, mixing like, they might say, oh, we've all had this same coach in the past. Because of that, we haven't actually practiced together, but we all have this shared strategy space. Let's use it. And so what's happened over the last 15 years or so is there's been a bunch of point solutions to ad hoc teamwork that make different assumptions, like they share a language, they don't share a language, they've there's the teammates are more capable than you, or they're less capable than you. And one of the open challenges, I think one of the exciting challenges in ad hoc teamwork now is trying to put those all together into sort of a grand unified theory of how would you put a ad hoc teamwork agent that's able to use, to do all of those things and also figure out what its current setting is in. And so that would be the mixing of these. And that's a good idea. Thank you.
Thank you. Let's thank. Now we have the next invited speaker, Katia Sycara. So let me pull up the slides. Okay, so we have the honor of having Professor Sycara from CMU. She has been doing, for a very long time, work on multi-agent systems, very broadly defined, right? So software, robots, human, and she has been, in fact, also a founding member of, one of the founding members of the International Foundation on Multi-Agent Systems. So I think it's a great honor to have her here. And today she's gonna talk about trust in human and swarm collaboration. Yep. So let's welcome her.
So hello. So in the interest of time, I'm not going to present an introduction about my work because that would take some time. People can find all this information. And so here, I just want to say that with respect to some of the work that Peter Stone mentioned, that's great work. And so we have done some work, and in particular, we are interested not only in ad hoc teamwork, this is not what I'm doing here, I'm going to present, but basically ad hoc teamwork between humans and agents. So the point is, the moment you have humans there, as we know, they're totally unpredictable, as we see in society and various and sundry other things. And so now you cannot even train ahead of time and say, well, these are the ones out of the population of the policies that they are going to do, because they are possibly not going to do that. And so the point there is, how do you do that? With unknown humans. How do the agents do? And so we've done some work on that you can find. And basically, we do pre-train, of course, like Peter mentioned, a library of policies. And then when we have humans, then we say, okay, what's the closest policy or other kinds of things? Or pre-training in current work on, we are using diversity quality types of algorithms to actually generate libraries of very diverse policies that are akin to human. In other words, this quality diversity has human characteristics. These are called human simulacra. And we have a big project from DARPA on that. And so on. So these are some of the things that are interesting. And by the way, we're also in that. And other projects are using LLMs now as ad hoc teammates, right? So now the point is, when you are telling LLMs, this is the setup, and please collaborate this way, or you let them go and see what emerges. And there are interesting things that emerge. And tomorrow I'm presenting in another workshop on LLMs, and I'll discuss some of that. But today, for here, what I want to do is look at modeling trust in human swarm collaboration. And this is work that came from a center of excellence from the Air Force that I had for trustworthy human autonomy collaboration. And so we all know about swarms, and they've been in the news about, Ukraine and so on and so forth. The point is, of course, all those swarms are not autonomous. All these drones, they are controlled by humans. And here, what we are assuming is that we are going to have, and we've been working on algorithms, control algorithms for swarms that are autonomous. So now the question that we want to study here is not only how to have these control algorithms, but also to be able to have humans that are going then to be interacting with these autonomous swarms, and how do they trust or not, and how they may be able to interact. So why do we want to have humans in the presence of swarm applications? It's because they can mitigate faults. Things happen, as I'll show, motors fail, things may happen. And also providing new task goals. You may have trained a swarm for a particular, for example, for foraging, and then you say, okay, now something happened, and I want to redirect now this bunch of drones, autonomous drones, to some other goal, because the mission has changed. And so you need a human to do that. Okay? Before, obviously, we have such autonomous systems that are able to look at the situation and say, now the mission has changed, let me autonomously change my goal. But that hasn't happened yet, so we're assuming that we're going to have humans. And so what is the idea then of this trust? And the idea here is that we need to be able to calibrate trust in humans and control of swarms, or in any human and autonomy collaboration. And so why is that? Because people rely on automation. They trust and do not use automation they don't trust, right? And so this is under trust. The human does not rely on the automation even when its behavior is correct and it could be beneficial. And it's over trust when human relies on automation even when its behavior is not correct. So this is necessary for calibration. Now, and so our overall goal is to determine this correct trust calibration, and the first step is to say what determines trust in swarms. So now let me see if I have a thing about swarms. Okay, so let me talk a little bit about swarms. What are swarms? Swarms are multi-agent systems, but each member of those systems is very simple, and it is controlled by simple control laws. And these simple control laws, like rendezvous and dispersion and so on, so their behavior emerges via these simple control laws. And and usually what the emergent behavior is by consensus. That means that each swarm member looks at their neighbors, and then what happens is it says, okay, here is gets messages from its neighbors about their position, their velocity, and so on. And then it averages this and says, okay, now this is what I should also do the average. And then this average propagates to the rest of the swarm, and they eventually do the right thing. So for example, they can all align their heading and their velocities to go somewhere. And that is called, foraging, or not foraging, but this is going to a particular goal, okay? So this is just and there are the control algorithms and so on that I'm not going to talk about. So what is trust now? Trust is a very slippery slope. Trust cannot be seen, but trust is everywhere, okay? You come here in the morning and you trust that there will be the organizers, there will be the speakers, there will be a room, there will be all these things. You haven't seen that before, but you trust. So what I'm trying to say, trust permeates everything, right? Now, in particular, in human, and automation, the trust in the psychology and all that, and there's been big literature, is basically what they basically have come now to define is an attitude of a trustor that depends on somebody that the trustor does not know, that is uncertainty and also vulnerability. So I'm willing to come here, to spend time, spend money, to come here trusting that there will be a conference, that there will be a room, and so on and so forth. I'm the trustee, right? I'm vulnerable because I've spent my money, I spent my time. And that's the whole point. I'm putting myself, okay. So trust is dynamic. So for example, if I see my machine not behaving very well once, whatever, I'll say, oh, forget it. I won't trust it. But then if it somehow or other, corrects itself, I say, okay, I'll trust it again. Okay, so it's dynamic. And then trust in models in human-robot interaction that have been up to now, say they are influenced by task performance. So if I know, this is another word, the reliability. If you're a reliable machine, I will trust you. If you're not reliable, so it's performance. Now, and they trust changes are readily detectable, right? My machine sends my email trustworthily. I say, okay, I can see that the email went to somebody else. But in terms of swarm interactions, these things are not so easy. Swarm performance cannot be automatically discernible to humans, we will see in the simulation, because I have 1,000 robots and they just go here and there, and humans, it's not so detectable what their performance is. They cannot take direct control to drive the swarm, in other words. I cannot have, and can give commands to repair swarm when heat trust is low or to change goals. So there, in other words, there is also a confusion in terms of now when the human is giving an input. Is this input going to repair or to direct the swarm goals? And so this is our overall actually model, the human trust in swarms. So there is some kind of observation of swarm behavior, predicts and communicates changes on trust level. Okay, so we need to be able to understand what is the trust level to start with, and then the response of the swarm, that's on the human side now. Then the response of the swarm is, once there is a decreased trust level, if the trust level is fine, it's okay, the swarm doesn't need to do anything. But if there is a decrease in the trust level, then it needs to increase its transparency. And by sending messages, we've done another piece of work on that I won't talk about, but this is in other words, telling the human more, try to make itself understood, legible, if you wish. And the other thing is detect and repair faults in a distributed way. And this is what I'm going to talk about also today. So I'm going to talk about the first bullet here, the first box, the human trust disorder, and also these detect and repair faults in distributed way. And then on the other hand, you can also have the swarm's trust in the human, right? Because a lot of times the operator may be confused, the operator may be stressed out, the operator may not be able to predict correctly, and so on. So now and give input that may not appropriate, and the human response. So what is the point? The point is this is a feedback loop. Okay. And so what we like is if we are able then to have a pre-trained trust model. Why is that? What is that is now suppose that I have an operator and it tries to interact with his swarm. The point is if it is a very intense kind of situation, we do not want the operator to be able to say, okay, now let me see what the trust is and let me intervene or not intervene and so on, because there may not be time. So the idea is it the case that if I'm able to create a model of trust of humans that is able to automatically, in a situation that is time critical, to put in the back end of my machine, and then it's able to see from my behaviors, from my inputs, whether I trust it or not, and then do the rest without me now telling it explicitly, I trust it. I just do the control things, trust prediction, revise the control. That's the idea. And so now what we want to do is to identify factors that affect human trust. Up to now, in most of literature, 99.5, whatever, whenever they do that, they give a survey at the end of the thing to the human to say, oh, did you trust or didn't you trust? By that time, human probably has even forgotten what they were doing. So the idea is it possible to do this online? But we don't want to interrupt and ask people, now do you trust or not? Okay. So now we want to see how we are doing that. And so what we did is we had this kind of simulator. It's a CUDA simulator with 200 robots, 200 members here. And we had the task is to find targets. It's a foraging task to find targets in a known area by giving headings to a swarm for a flocking behavior. So it flocks towards a particular place, flocks together, and then they try to find. So now the task performance is the number of targets found. And here I'm just showing a depiction. So we did experiments even with showing the performance, the number of total targets found as the swarm is going around. And so this, what we have at the beginning is a black thing, right? They don't know, it's a search task. So we see them going around, and you will see that in the simulator. And then the swarm is going to unexplored areas that it needs to find these little targets, the green things that it doesn't know. And then the operators try to direct it to the best they can. And so this is the simulator. I hope it works here. No, it doesn't work because this is not on my machine. And I think that's what's happening when one is, I didn't think about that. But anyway, sorry, because I put my, okay, sorry. Okay, so the point is this is the simulator. You can see the black thing, and as the person is putting from the keyboard is putting input there to direct the swarm, then there is a panel here with the trust level, and the panel is like a slider that automatically goes up or down in directing the trust. Okay. So what did we see here? In analyzing these results after the simulator is that the length of command vectors of the two types of commands, repair, change goals, so which was very strange, a statistically significant difference. So that means that we were first able to differentiate these two different command types. Okay, and so the one was longer than the other, significantly longer for one of these things. And then trust is highly correlated to heading variance. Here I show, and the convex hull area. So when interventions are issued, the heading variance is larger, and the convex hull is smaller than when interventions are not issued, and task performance is less influential in the physical states. So what is interesting is although we were showing them the performance, the task performance, how many targets were found, and in what configuration, the person could see the performance and the state of the swarm. However, the correlation and the significance was with the heading variance and the convex hull rather than the performance. So that is kind of interesting and counterintuitive and counter to the previous literature. That's why it's worth, because people are very much influenced by kind of what they see in pictures. And so what we did is we used these findings to construct a Markov model where the state variables are the heading variance, the convex hull, and the type of intervention, and then use reinforcement learning, inverse reinforcement learning, to find the underlying reward function. Using this IRL then, by finding the reward function and then running the reinforcement learning, we were able to predict. And so we use this model now. We ran it with humans. And what you see here is a little sample from 10 of our subjects. We ran, I think, about 50 or 60 subjects. And this is a snapshot of 10 of them. And what you can see is the prediction and the user feedback. In other words, in terms of this slider, are very, very well going together. And so the idea here is that one could use this model in the absence of the particular human to actually direct the seeing what the human is doing. The model sees as input what the human is doing, and then it calculates the trust, right? And then it can revise the control. That's the idea. The other thing that is interesting is that trust is more so each person has different patterns of trust. So I cannot take this, and that's why I'm presenting here the various individual ones, because it's not that I can take an average and say this is the average trust. There's no average trust. There is individual differences there. So another thing that I want to, the second part is the second thing that I was talking about in terms of now if the trust is low, how does the swarm repair itself, okay, and change itself so it can be more trustworthy to the human. And so here, what I will talk about first is vulnerabilities of swarms, and second, human experiments that we did with induced faults to actually find out how these things work, okay? So what is the nice thing about swarms? The nice thing about swarms is that they are robust to the loss of their members. So if I have 100 and I lose, 5 or whatever, it's okay, because the rest are going to go get their goal, do their goal. So that is very nice. On the other hand, if I have multi-agent or multi-robot systems, I have 3 of them, and each one of them is highly sophisticated, and it thinks, and it does these things. I lose one, then it's problematic, because now I have to redo the role allocation to the remaining ones and so on. So it's a different story, okay, with respect to swarms. Okay, so on the other hand, so we said that they are robust because they are running consensus algorithms and immune to noise and random disturbances. On the other hand, swarms are highly sensitive to spoofing or damaged members. So we will see something like that. So there could be variations. So usually when we have the swarm, the different members could have different headings, different velocities, and so on. So they are all over the place initially. You can look at them and say, okay, what are they doing? They're sort of doing random things. But then through this consensus formation, then they could actually do this flocking and align the heading and their velocity as an emergent behavior after these many rounds of collaboration. Okay, so what is then the self-repair? The self-repair is the weighted mean subsequent reduced algorithm. It's a mouthful, but it provides a way for behaving in such a way as to quarantine and isolate members of the swarm that are faulty. Okay, so at each node, you can imagine values furthest from one node, because we said with my neighbors now, every time I get the position and the velocity, and I compare it with my other, and also I form the average. And so now if this is a faulty one, at t equals 1, I say, okay, I have this distance, this is my position, this is your position. At t equals 2, I see your position becoming bigger, and I say, well, I'm not so sure. Let me reduce his influence a little bit. And then if you go further, and I see that it's really not going towards a consensus, but it's, for example, getting further and further, then I reduce for myself your influence. And so eventually, it's not just myself, but everybody's doing the same thing. And then eventually you get isolated, the faulty one gets isolated and does not affect the performance of the rest of the swarm. And so this offers also performance guarantees. Let's see where we are. We started late, of course. And so the point is then that we adopt this mechanism, and the idea here is that, decrease velocity and so on. So you can see here is, I don't know why this thing is showing. There's this band there. So here we show some a particular situation where we have a motor degradation in a robot with 6 robots, and we have robot degradation in robot 1 and robot 4. the red and the very bright green here, the two of them. So if I have the normal status and they are trying to do flocking, you see in terms of the trajectory, at the beginning they are starting in all over the place in terms of their trajectories, but eventually they converge to a same kind of trajectory, all in parallel so that they can flock. Okay. In terms of the velocity, again, you see at the beginning the velocities are all over the place, but then eventually they are more or less the same. The heading direction is kind of the same and the connectivity is high. Decreased velocity, so now suppose these two, robot 1 and robot 4 have decreased velocity. So what does that mean? That means that they stay behind. They cannot follow the rest. They cannot merge adequately their velocity. They are degraded. Their motors are degraded and they have little velocity. So what you can see here, then instead of the normal status thing, that should be this, this almost, horizontal line, right? That's the correct one. You see it goes up. That means now it's really has been influenced and is doing the wrong behavior. And so you can see down here in the actual velocity that we have the red and the green. They are kind of outliers, whereas all the other ones have converged. The same thing for the heading direction. The communication is very low. Now, when it's corrected with our algorithm, what you can see, although the red is down there kind of as an outlier, the rest of them converge. That means it has repaired itself. And the same thing for the other. You can see that now have sort of repaired themselves. Okay, so that's the idea here, that they repair themselves. And so now it restores to swarm to sort of correct consensus. And the point is, what is the effect of these, first of all, injecting the faults for the human's trust when I observe as a human this behavior of the swarm, and what is the effect of my trust to the swarm with respect to a repaired situation? Do I recognize as a human that now it's a repaired situation? And so the questions is, what do we see? These are the questions for the experiment. And so we did an MTurk experiment where what they did is they had small videos. They saw in these small videos swarm members as dots that were moving, okay, towards, they had the consensus algorithm that we had developed, of course, and they were moving towards consensus, and they were asked to rate their trust at a 5-point scale. Don't trust at all, distrust, neutral, trust very much, and to answer some additional questions about individual swarm members, whether they also trust individual ones or not, and so on. And so the trials were presented in a single randomized order to all participants. So the way that they saw the sequence of normal, faulty, and repaired was randomized. And so we had 14 trials for each participant. 2 of them were normal swarm behavior, and the others were faults that were injected and repaired, the other 12, okay? And they all shared the same initial condition. And so what we found is that, first of all, so what we saw here is that from the faulty, in the situation where 1 was faulty robot out of 6, we saw that the people were talking about neutral in the faulty. They did not say trust, because the point is these people were seeing these little dots moving around. For 6 of them, and many dots moving around, and then the 12, many dots moving around with various faults. So it was not a very easy thing. I mean, I showed these nice little curves, but they were not seeing the curves. They were seeing these little dots, so it was not an easy task, even for humans. That's the idea. And so they went from neutral to trust. This is significant, okay? And as you can see, is less than 0.001, the P. And the motor, if they had 2 out of 6, they went from distrust to neutral with a repaired. 1/2 from trust to trust, plus, right? They were able to recognize if 1 out of 12 was. It was not significant, but there was a difference, right? The P was 0.6. And 2 from 12, again, neutral. They were neutral now. 2 out of 12 are wrong. So they were not trusting, but they were neutral. They would say, well, we're not distrusting. And the same thing, we can see these things here. And so here what I see is a scenario. So we had these different types of things where motor failures and also wind. And wind, of course, is going to take the swarm from, each of the members. Of course, they're going to change directions and things like that. And so here what we show is a scenario with 12 robots and wind situation. And we have the trust level on the y-axis and normal, faulty, and repaired on the x-axis. And we look at that, and we see that initially for all of the 12, when they were doing well, trust was good, was high. And then in the faulty, you see how it falls, although for a couple of them, still the trust was high. And then for the repaired, it goes somewhere in between. And so this is the overall, conclusion here, that people are able to trust, to see, even in these kinds of not very obvious conditions, to see when the swarm is operating in a normal situation, and their trust falls when they are able to see when it's faulty, and also they are able to go in between because the question that we ask them, not only do you trust and so on, but also would you reuse? Because the point is, would you continue, to use that? Would you rely? And so what we have here is there are other. So we looked and said, okay, what are the other contributing factors? So we asked them to explain the reason for their trust assessment. And so for the motor situation, 18% of the subjects says it was the wrong direction. They saw that it was going, the wrong direction. That's why they didn't trust it. 60% said they noticed that there was inconsistent speed, which is basically the correct thing because the faulty ones had decreased speed. And 22 said, well, poor compactness, so they were paying attention to something else, right? For the wind, 67 of them said wrong direction, and that's correct because the wind was, of course, shifting them into the direction away from their goal. And so people were able to really even see what the reasons for these faults were, and the overall, this is the thing. So that's interesting. And so here, what we did is another one is to see how the degradation of the swarm, it's another, I think these are all papers that we had. So it's another situation that we wanted to see is what is the number of faulty robots in a swarm that would make people change their judgment from normal to faulty. That's very important in, of course, situations like crisis response and so on when you have damage. So 47 participants, they saw pre-recorded, now this is a foraging behavior where they're trying to find targets. It's like the one that I was not able to show the video, but anyway, the point is that they spread out and try to find targets. And they degraded the cover story. What the participants were told is that they shouldn't cross no-fly zones and they are influenced and so on. And so the point is that we degraded the swarm by 5% of the members, 10%, 20, 25%, and they rated their intention to rely on the swarm. That means that shows trust. And the results show that the significant reduction in intention to rely judgments came between 15 and 20. So there was a drop between 15 and 20, and then it stabilized. And so here are the conclusions. I presented this, and we showed this IRL-based model that could be something that could be used now in time-critical situations when instead of the person having to stop and say, what is your trust, what is your trust, if one has created a model, an IRL or some other kind of model of that trust of that particular person, then it could be used to do these trust assessments instead of asking the person every time. And this algorithm that I talked about preserves swarm consensus and reduces the loss of trust. And now we have performed some additional experiments with more realistic environments. I don't have time because they're more complicated, you know. And one of the things that's interesting is that we would need, you see, the motor failure is a permanent damage. The wind is a transitory damage, a transient, because if the wind stops, then the rest can be okay. And so although the algorithm, the repair algorithm repaired both conditions, it may be for further work, it may be interesting to look at these kinds of things for transient kinds of phenomena, like the wind, and permanent kind of phenomena. And so, again, potential trust repairs, here I'm talking about some additional things that are kind of open problems and for further research. And I think this is it, and these are my collaborators and students and so on. Thank you. Any questions?
Run a little bit later, but so like maybe one question.
Yeah, this is probably unfamiliar for most people because swarms are not something, and especially human, it's just maybe by now 4 or 5 papers. I mean, it's a thing that's very understudied, and especially in general, trust, human trust in multi-agent systems. If you look at all the papers in the literature, almost all are one human, one robot. Okay, oh, do I trust you to go this way, the manipulation and so on and so forth, 1 and 1, not even 1 and 5, and let alone 1 and 100.
Well, thank you for a very interesting talk. One of the distinctions in the use of trust that I have come to believe is important is between trust in a mechanism or an inanimate object versus trust in an agent who is pursuing goals.
Yes.
And I think that's actually I see that as a very important distinction. And I was wondering to what extent that's reflected in the way you're analyzing trust here.
Yeah. So the thing is, one of the you're absolutely correct. So most of the work on trust had been the human factors and literature in particular, where they were looking at trust in automation. And there is a long history from 1988 in Urbana-Champaign and so on, and also Parasuraman did a lot of work on that. And there you had automation, not autonomy. And so this is where a lot of these initial results about performance, reliability, and so on came about. Now, the moment you have automation, you have, as we saw, different elements, and this is one that is not antithetic, you know, it doesn't conform to the previous literature because now we have autonomy. And the other thing is the dynamics of this trust also, because if you have an autonomous system, it probably is going to behave in a more nonlinear kinds of ways than if you have just simply automation that you pre-program. And so the dynamics of that is also much more nonlinear. And so the idea then is that in terms of the humans, now they have to cope with these very more dynamic kinds of situations. And that is why it's very difficult. I mean, in the literature, again, when they said, okay, the human and the agent, you can ask the human, or they had this subjective, responses at the end of the experiment that they were reliable because the automation was a much more predictable thing because it was pre-programmed, although it's adaptive automation and so on and so forth. Here, that's why we wanted to do, online because of this more dynamic nature. You're right. And there are all kinds of other issues. I mean, if you're talking about trust between humans, that's another thing, because then also, of course, there is these issues of betrayal and so, I mean, escalation and all that kind of thing, emotional responses and so on and so forth. That is, if we want to endow our automation with this, which we may, then we would have yet another big can of worms. Yeah. Okay.
Thank you. I think now we're gonna have a series of talks from the contributed papers. And let me pull up the schedule over here. So the first one will be innate values-driven reinforcement learning, which I think will be this one. And all the other speakers, like, can ensure that you uploaded them on Google Drive, or please reach out in case. And so this will be presented by Professor Young.
Okay, thank you very much. So my paper is Innate-Values-driven reinforcement learning. So I'm very fortunate this paper is belong to one of the fundamental research program supported by NSF. And yeah. So actually I will introduce this kind of the idea in 5 parts. First, I will slightly discuss the introduction part. So actually, when we studied, intelligent agent, especially humans, want to pursue some specific goal, we start from the psychology side. We studied their motivation. Actually, whatever kind of the creatures like humans, the animals, that they doing things that is driven by their motivations. We can, from another perspective, we just a certain kind of a blend of the motivations, the entities. So here, like we said, in the nature system, the motivation is concerns the absolute with the activity of creatures as reflect the pursuit of the particular goal and form a meaningful new units of behavior in their function. So actually, we can that we have a intrinsic motivation, also like the curious and activement and curious, and also have the extrinsic motivation, like the punishment, grace, and prize. So like we discussed, the human being just like the blend of the motivation, which means the combined motivations together. So actually, those kind of the motivation can also can analyze from the the needs perspective. So it's one of the very famous theories in psychology is the Maslow's needs hierarchy. So this Maslow's hierarchy just describes our human being separate the humans needs in a five level. So each level for example, in the lowest level we have a psychological needs. We want food, water, and sleep to support our normal function. And when we satisfy the low-level needs, we want to safety needs, find a shelter, a house. After that, we want to pursue some social belonging, and the high-level needs, we want to self-achievement. So actually, like we said, the human being is a blend of the this kind of needs. So also our needs is dynamic changed according different environment and interaction. For example, currently my needs just give you us a presentation, but right now maybe I'm also hungry, I'm also thirsty, but currently I know my priority needs is to finish my talk. So those needs also the conditional dependency. Okay. So yeah, this is the like we said, the basic theory of how to, from the psychology side to describe those the needs hierarchy. I mean, describe the humans or creatures the needs. I mean, so those needs also, conditional dependency, like especially the hierarchy, like the psychodynamic. In the lowest level needs, which means that we folks describe the who we are. When we satisfy our levels needs, we will become ego, and then we will collaborate through a collaboration with each other in the multi-agent system, like the human society. We will have the identification. Then after that, we will achieve our dream, like the self-actualization, become super ego. Okay. So that is the basic idea why is to describe the humans, the motivations. But here is the key problem: how to finalize this kind of model and implement like the AI domain, robotics domain, and especially to build a certain mutual understand architecture between the AI agent and humans. So okay. So the key here, I just briefly discussed some background about the those intrinsic motivation model. So here is the foundations of the to formalize the AI agent. The intrinsic model motivation model is the it's listed in the reference paper right by the Katia in the 2016. It's very easy to understand, I believe. First, like the sensors gather the information, then through this information from the interaction and the environment, first we will base on the individual intrinsic motivation component, which means that every agent will have their unique value system to make a decision. For example, every time we receive the same message from the interaction and the environment, but based on our current, the priority needs, we will, according to this information, make a decision. Maybe some, for example, right now, I provide a food for you. Maybe right now, the other guy is hungry. Okay, I will take the food, but the other guy already satisfied their low level needs. Okay, I'm not hungry right now. I might find some water, and maybe I will go sleep, and maybe I will study. So different people, when they receive same information, same interaction based on their value system and the corresponding domain needs, also will have a different feedback and the behavior and strategy. Okay, that is the real happen in our current real world. Okay, so that is the typical model. Through this unique value system, we will make a decision for current situation. Then we will, through the actuator, to execute the current, the strategy and actions. So, so the preview is the basic model to model our this kind of the needs behavior, but how to quantify those needs from maybe from the economist perspective, the utility theory, especially the expert utility theory is pretty common and frequently used in quantify. Those kind of the needs. Okay. According to this previous discussion, here we just proposed a new approach we called Innate-Value-driven reinforcement learning. Since the I don't know what is wrong with this picture, but I just slightly discussed the basic idea. So for the traditional reinforcement learning, the agents just perform a behavior, a strategy to interact with other agent or environment, they get the maybe feedback or reward directly. But actually, this feedback or reward, maybe every agent, especially multi-agents, will be same. There will no bias. But in the real world, especially in the human societies, everybody maybe have their perspective. I mean, their unique value system to analyze every feedback from the environment and the interaction. And based on their unique value system, they will give the suitable strategy and action to interact with other agents. So that is to make anyone is the different and anyone is the unique. So in that way, in the Innate-Value-driven reinforcement learning here, when the agent performs a specific action to the environment, the feedback is not traditional reward, but utility, which means that every kind of the the utility come from the environment. Then go to the agents, the Innate-Value system, which means we use the previously discussed expert utility series. We have a needs weight and the utilities, the needs weight metric, and also have a utility metric. And through this kind of the metric, time of the metric, we can build a certain kind of the metrics to analyze. We discussed about the needs hierarchy. Okay, I hope so. The key difference is in here. Use this model to describe with this previous needs hierarchy. So here the expert utility theory is that we have a this is an expert utility theory, and we have a needs weight, and we also have a utility from the environment, and finally we can calculate the reward. So the reward is slightly different between the traditional reward we directly get the environment. So this is the time is over. So this is the source of the randomness. Compare the state. We have first we have action, and we have needs weight. Finally, we calculate the reward. Follow this kind of the strategy trajectories. And here I list several how to formalize our model and how to implement in the Q-learning function. This is how to implement the IVRL in our deep Q-learning models. And here, and we choose the this game is Doom, playing the Doom, because the Doom you can customize your feedback based on your requirement. And here I just list and also implement in the actor critic models. So as you can see here, we have a two direction. One is generated the behavior, the other is generated the weight of the needs. Then we calculate our final result. Yeah, evaluation. So compare with, so we just compare several scenario like in the VIZ Doom games, like the defend the center, defend line, defend the corner, and antenna. And finally, we find our method will achieve a great performance, especially consider the different situation. I mean, like this scenario, through this training, the environment just training agents coverage to a certain kind of the needs weight and represent specific personalities. So the time is almost here. So yeah, I just quickly do the conclusion. Actually, this is a prototype of the, very prototype the concept of the IVL. We will future might be implemented in the multi-agent system, the real-time strategy and human, especially the human robot interaction, build a mutual understand architecture between AI agent and robots.
Great, we can move forward. There's going to be the coffee break, and you're welcome to ask a question. So we have afterwards, the second oral talk is going to be what are you saying? Towards explaining communication in multi-agent reinforcement learning. Do we have Cristian Morasso or the? Oh, okay, go come here. Okay. Yeah.
Working from Google Drive. Okay, thank you very much. My name is Daniele Meli. I'm a researcher at the University of Verona. And the work of today, which you can see also the poster there on the right, is a preliminary study on explainable AI, and in particular using explainable AI in order to understand, to have a deeper insight and explanation on what the agents communicate between each other during multi-agent reinforcement learning enhanced with communication capabilities. So, just a very brief introduction. We are talking about multi-agent reinforcement learning. All of you know. The typical approach to multi-agent reinforcement learning is to have the scheme of centralized training and decentralized execution, where in the centralized phase, the agents are trained all together, and then the policy is split among the agents during the execution. And typically, one of the problems in this setting is the non-stationarity. Which means basically that, of course, the policy of the agents during inference depends on the different behaviors of the other agents and their interaction. And so one opportunity which was proposed in literature to address this problem was to introduce the communication capabilities for agents. There are different approaches to this. In particular, in this work, we consider the approach from 2016 of REAL, which is reinforced inter-agent learning, where the idea is that the agent learn a communication message, which is then exploited during the inference phase. So it's like learning both the classical actor policy and then the communication policy. What is the problem of this approach is that, of course, when you learn the communication protocol is another black box layer into the pipeline, into the framework. And so the goal of this paper is actually to start investigating how to explain the communication that the agents are learning. And this can be useful for a number of reasons, also for devising novel model-based communication approaches in the future. So, in particular, how to explain the communication behavior of the agents, we resort to two main approaches from explainable AI. One is the integrated gradients approach, which basically allows to extract the relevant features inside, for instance, a network, a communication network, or a policy network. And then the causal discovery approach, which allows to discover causal relations between the features and the actions of the agent. So the integrated gradients is basically a relevant feature extraction approach, where you start from a neural network f theta, depending on some parameter theta. And then what we want to assess is what is the effect of varying specific feature inputs on the output, actually, of the network. While in causal discovery, what you typically do is assessing the causal independence between variables, which is measured by a standard metric, which is the conditional mutual information. It is not, of course, the key of this talk to go into the details, but just the idea is that you kind of measure in causal discovery what is some sort of transfer entropy between some features and the others, so the features and the actions of the agent. And the conditional mutual information measures exactly this information, which is on the bottom part of the slide. And the idea is that if the conditional mutual information is null, then you have that actually the features are independent, and then you can remove basically the causal connection. So in the end, you end up with a causal graph like the ones on the top, which specifies which feature is connected causally to another features both in space and time. So you end up with a causal graph. Now, how to apply this to the problem of multi-agent communication and reinforcement learning? Well, we start actually from a very simple domain. Again, this is a preliminary study from a master student, which is the simple spread domain. The simple spread domain is the one on the left, where basically you have three different agents, which are the colored balls, who have to move towards some targets. The point is that the agents only have to perform the coverage, which means they have to cover all the targets. There are not predefined targets to be achieved. And so the agents have to learn to coordinate in order to avoid collisions and at the same time perform the optimal coverage. And what we did was testing different approaches, multi-agent approaches to this problem, in particular based on multi-agent DDPG. We tested different communication protocols in particular, where the first one is the learnable approach, where we actually let the agents learn a communication with the real. And then we go to some model-based approaches where we explicitly define the communication messages. So just to go very quickly, first of all, we notice, as expected, that the use of communication, in particular of the learned communication, allows, in the orange curve on the left, to reduce the non-stationarity problem and then basically to have better and less varying training performance. And then we try to assess the explainability results. So in this sense, we first try to evaluate what is, from a relevant feature perspective, the impact of communication on the policy. And we notice that actually the communication doesn't really affect the actual actions of the agent with the integrated gradients approach. But then if we go to the causal analysis, what we notice is that when we consider, for instance, two different communication protocols, the learnable and the model-based one, we see that in the learnable protocol, which is the one where the agents perform the best, actually there is a causal connection between the features of the agent, in particular the communication messages, and the velocities of the agent, which actually leads the agents to better self-avoid each other. So actually with the integrated gradients, we are able to spot basically results about explainability, while with the causal discovery approach, we are able to to explain what we are actually seeing in real life, which is on the left, the agents better avoid each other. For instance, in particular, the green and red agents do not collide between each other and do not approximate too much. So this concludes the presentation. Again, this was a very preliminary work. We are going to test on different algorithms and domains, but it was just a feasibility study of explainability of explainable AI for understanding multi-agent cooperation and communication, also from a perspective of cognitive science. Thank you.
Thank you. Okay, it's going to be coffee break and post the session. So perhaps we can so which is incentive design in hedonic games with permission structures. Okay. And did you upload it? Oh, this one.
Hello, everyone. My name is Yuta Kahoshi. I'm from Kyushu University in Japan. The title of my presentation is Incentive Design in Hedonic Games with Permission Structures. This is outline. First, I'll talk about background of my research. A Hedonic game is a game that forms a collision structure based on the preference of each agent, each participant. Forms a collision structure means agent set divide, say, some groups. As shown here, various models of Hedonic games have been researched, but in existing research, there is no model that incorporates information diffusion into Hedonic games. And in cooperative games, there exists a model called the permission structure. This is a model in which an agent must obtain permission from agents already participating in the game to join the game. Permission can be considered as an operation where an agent invites another agent, allowing the model to be regarded as one of information diffusion by agents. It is used when discussing the incentives for information diffusion in cooperative games. I'll explain the overview about this research. We introduced a permission structure into symmetric additively separable Hedonic games and examine the information diffusion by agents. Specifically, we examine the compatibility of agents' incentives for information diffusion with other well-known properties. And we analyze the utility of a mechanism that satisfies the incentive for information diffusion. Now, I'll talk about the models used in this research. First, I'll talk about existing two models. The first one is a symmetric additively separable Hedonic game, SASHG. It is a Hedonic game represented by a weighted undirected graph. In this game, the edge weight represents preference between agents, and preference value for each other are equal. And the utility of each agent is defined by the sum of value for agents in same group and same collision. And a social surplus defined by the sum of the utilities of all agents in the collision structure. And a more social surplus is considered a better result. Another existing model is permission structure. This is the parent-child relationship between agents represented by a directed graph. In this model, to participate in the game, agent must receive permission from their parents. There are two models in permission structure. A conjunctive permission structure is agent must obtain permission from all parents to participate. And disjunctive permission structure is agent must obtain permission from at least one parents to participate. In this research, we propose a new model called a symmetric additively separable Hedonic game with permission structure, SASHGPS. This is a Hedonic game defined by the utility graph G and the permission graph H. The utility graph is undirected weighted graph, and the permission graph is a acyclic directed graph. In this game, first each agent grants permission to other agents, and then the agents that can participate are divided into a collision structure. We also define incentive compatibility. Incentive compatibility is a property that it is optimal for agents to act truthfully. In this research, we defined the following two types of incentive compatibility related to information diffusion. Dominant strategy incentive compatible, DSIC, is regardless of the action of other agents, it is optimal for an agent to grant permission to all of its children. And ex post incentive compatible, EPIC, is assuming that other agents grant permission to all of their children, it is optimal for an agent to do the same. And we classify incentive compatibility in each of the two models of the permission structure. For example, DDSIC in conjunctive permission structure called CDSIC, and in disjunctive permission structure, DDSIC. CDSIC is the most strongest permission incentive compatibility, and DEPIC is the weakest incentive compatibility. Next, I introduce well-known properties that are focused on in this research. Nash stability, NS, is the utility of each agent does not improve by moving from current correlation, and the individual rationality is the utility of all agents is not negative. And Pareto efficiency is no agent can improve their utility without decreasing the utility of other agents. And the freeness is no agent can improve their utility by swapping correlations with another agent. I'll talk about the main result of my research. In this research, we examine information diffusion in Hedonic games from the two perspectives. First, I talk about analysis of the compatibility between incentive compatible and other properties. Regarding this, we presented 4 theorems. Yeah. Theorem 1, there is no mechanism that satisfies the DDSIC and Nash stability. Theorem 2, there is no mechanism that satisfies CEPIC or DDSIC, and DDSIC and Pareto efficiency. Theorem 3, there is no mechanism that satisfies DEPIC, Pareto efficiency, and individual rationality. And theorem 4, there exists a mechanism that simultaneously satisfies individual rationality, MB freeness, and CDSIC. Here is a table summarizing that result of theorem 1 to 4. The existence of mechanisms that satisfy Pareto efficiency and DPIC remains as a future work. Next, examine the performance of mechanisms that satisfy incentive compatibility. For evaluating the performance of mechanisms, we define the approximation ratio. The approximation ratio of mechanisms defined by the approximation ratio of social surplus in the correlation structure returned by the mechanisms for the worst case input. As a first result, the approximation ratio of any mechanism satisfying DPRC is 0. DPRC is the weakest incentive compatible, so this is a very negative result. As a natural question, is it possible to improve result in the restricted test SHGPS? We consider 2 types restrict SSHGPS. The first one is restricting grass structure to a forest. In this case, there exists an optimal CDSMC mechanisms. Next. And another case, I restrict the edge weight to only -P and 0 and P. In this case, the upper bound of the approximation ratio of any mechanisms satisfying either DDSIC or CPIC is order 1/n, and there is a polynomial time mechanism that satisfies DDSIC, and the approximation ratio of that is order n. My research conclusion is here. Thank you. Yeah. Oh, sorry. Thank you.
Okay, so the next talk is going to be detecting adversarial inference in cooperative tasks through multidimensional Bayesian trust metric. And which one was the file?
This one. Yeah.
Yeah. Okay. Otherwise, I will download it and.
Okay, so this is kind of preliminary work done with one of my PC students who couldn't be here. Try to detect adversarial interference when you are playing a kind of cooperative task. So the main idea here is that often agents assume that the other agents are cooperative, but in fact they're not necessarily cooperative. And there may be different reasons why they're not cooperative. Maybe they're not willing, or maybe they have some kind of hardware problems, some other problems. And so we are proposing a trust matrix. I'm kind of interested in using trust that can be computed directly by the agents. So we come up with a kind of matrix so that the agent can observe what the other agent do and adjust their trust value that they have for the other agents. And this is in the context of kind of a Bayesian game theoretic approach. And we have a reinforcement learning agent that has to interact with another agent and make decision if the other agent can be trusted or not. We have very preliminary result. Again, this very, very preliminary work showing that, in fact, you can kind of detect in a relatively reliable way if we can trust the opponent or not. And we have a few examples done in the overcooked AI environment. Let's see if I can. Okay. So one of the assumptions we make is rationality. So expect that the agents will try to maximize their expected cumulative rewards. And there are, of course, at least two different kinds of rationalities, and is self-interested or cooperative when you try to maximize a shared objective. So just to kind of get into a little bit of examples, suppose you have two agents. In fact, in all these cases, we have only a pair of agents, and one is kind of a reinforcement learning agent, and the other one is a cooperative agent. And you can think about some kind of reward that you get for the cooperation that you can do. But now suppose that you come instead only 50% of the time, maybe you have a cooperative agent, and the rest of the time you have another agent who could be adversarial, so intentionally try to not to help you, or could simply be lazy. And so in this case, the rewards that the pairs of agents get is going to have to be different, depending again on the type of agent. Just a very high level overview of trust. So we kind of again use the kind of definitions of trust. They came out from earlier work, and we update the beliefs depending on using the Bayes theorem. So we kind of use a probabilistic approach to update the trust, and we have again a pair of agents. Everything has to be done in an automated way. I'm trying to skip some of the low-level details in the interest of time. There is a poster, so we can go over more in detail. So this is just to show an example, this is the overcooked AI environments. There are 5 different scenarios. There are 2 agents in each of them, and I have to, it's a cooking problem, so they have to chop onions and provide, the results to customers. And there are, again, different environments. We look at only 3 of those in which the agents have a kind of different layout of the space that they have. They always have those, you kind of see the onions that need to be chopped. Sometimes they have more space, sometimes there's less space. And they have to serve the customers faster. So this is kind of the general setting for the environment. And again, what we're trying to do now, if I have again a reinforcement agents, and we're not doing anything fancy with the reinforcement agents, but again, we're trying now to see if one of the 2 agents is not cooperative, what happens? And can we learn and can we figure out not to trust? So again, maybe I don't trust the other agent to chop onions, so I'll do it myself so the customers can be served. Okay? So the method that we use comes for modeling trust, comes from a system called Travos. It was developed a number of years ago. And basically there are two variables that are used to use a beta distribution function to model the random choices. And there are 2 variables called alpha and beta, and we can kind of estimate the expected values of the trust with the formulas that are written there on the side. So I have the agent, I have the other counterpart. I don't know if the counterpart is cooperative or not. And I have ways of measuring the trust, which again, is different depending on the type of other agent that I have. Let's see if I can move on. A few quick results. Again, this is very preliminary work. So again, this is what's called asymmetric advantages, which is one of the 5 environments that you use in these scenarios. And what we're showing, the training part, and we kind of compare the reinforcement learning, use DDPG, the reinforcement learning, what we call multi-travels, which is our extension, and the reinforcement learning with the simple basic travels. So travels is a system been developed maybe 10 years ago, and it's kind of a standard system for trust for agents. We extended it, we call multi-travels, because again, now instead of simply say, yes, I trust you or not, we tried to detect different kind of agents. So again, agent that can or cannot be trusted. Again, it could be adversarial or could be lazy. One of the applications we're looking for is to use this with robotics, in which real agents may not be lazy, but just, that something is broken and they can't do things. And can we kind of detect problems, harder problems in another agent, because again, using this trust model. So the top one shows the training part, the bottom one shows the evaluation part. It's hard to read it, but you can kind of see that over time, our approach, which is the orange one, which is the reinforcement learning agent with multi-travels, gets higher rewards than the other. Again, very preliminary results, but just to give you a quick idea. A second example is called the coordination ring, in which, as you can see, the agents have a kind of round area, and so they have to coordinate without bumping into each other. And again, we have kind of similar results. So, just in conclusion, we think that this is kind of a promising environment for dealing with complex situations. Again, it's kind of Bayesian game theory underlying, and we kind of use the ways of measuring trust that was proposed by Travos, but we have extended it by allowing to distinguish different kinds of trust, different kind of agents, and so try to assess if we can trust them or not, depending on the kind of agent that they are. And of course, this is very, very beginning work. We think this is kind of open and interesting areas, and hopefully we'll keep on doing more.
Thank you. And last, we have the talk towards multi-agent spatio-temporal error restoration by Amel Dosena. Just gonna open.
Hi, morning. I'm Amel Dosena, a PhD candidate from Dartmouth College. I'll present to you our work towards multi-agent spatio-temporal environmental property restoration. So consider an environment where there are like areas spatially distributed, each with decaying properties, and if left unrestored, would hit a critical threshold. And like F decaying below the critical threshold are like those are like undesired states. And then we have a team of multiple robots to accomplish this task, as like the cost of robots have markedly decreased. So the use of them actually has become practical. Moreover, they might be like the better option, especially in tasks that are kind of like hazardous for man preservation. We just want to find a schedule of visits for the robots, when to restore those areas and charge battery, so that the temporal properties are below critical threshold is minimized. So we coined this problem as the spatio-temporal environmental property restoration with multiple agents, multi-star for short. In our previous work, we dealt with the star problem, but for single agent. The multi-star, however, is still an open problem. We note that even for the single agent, it is NP hard, so was the multi-agent case. The related state-of-the-art solution, which is the orienteering problem with time-varying rewards, assumes that areas are to be visited at most once within the time window of schedule. And it has also like a different objective, which is to kind of like maximize the total collected rewards, which is different from our objective. So this has significance, in many real-world applications today. So for instance, in precision agriculture, in cleaning of water bodies and public spaces. So we propose a framework where it will allow human preferences, as well as like allowing the agents to kind of come up with decisions to restore the areas, as well as like ensure that they don't die during mission. So it is apparent that the areas can be clustered. So there can be attributes wherein areas can be clustered. So for instance, here it could be like the decay rates, how fast areas are decaying. The interdistance, that's also a possibility. Exogenous variables, that's also one. Or it could be just, like the human preferred variables, or, the human agents. We just want to cluster them as it is. So for instance, if I were the manager of this building and then I have a team of robots to kind of clean up the spaces, I would perhaps want to cluster the areas. Okay, there's a cluster of areas, let's say in the first floor, the second floor, and perhaps in the ballroom. So, yes. And then from here, from each of these clusters, we would then assign this to a robot, which is a divide and conquer approach, a typical approach, in multiple robot orienteering problems or task allocation. So when the agent receives, its assigned clusters, it would then translate the model decay functions into losses, which are inversely related to the decay. It will then search for a schedule that minimizes the total opportunity costs of visits, which is just the net of the losses, for the duration of the visit, as well as ensuring that, that it is kind of like feasible, the most efficient, resource efficient in terms of battery consumption. There's a limitation, however, as we mentioned, this is kind of NP hard. So the optimal solution, the full tree search or brute force, has exponential runtime. In our previous work, we proposed a heuristic algorithm that chooses the next feasible visit that minimizes the forecasted, the immediate and then the forecasted opportunity costs of visits. Employing this allows persistent restoration, of these areas in real time. Of course, we have to account for the reassignment of clusters and agents, as like we have different parameters that are kind of like dynamic. So for instance, an agent may become unavailable. Therefore, like its assigned cluster needs another agent to kind of take over. Another is like the decay functions may evolve. And so like, like those clusters should not be static. They should be kind of like dynamic as well. And other optimality considerations. So for instance, if I have a robot that is kind of like nearby a subcluster, which may not necessarily be assigned cluster, can we reassign that robot to that cluster, enabling cooperation, collaboration, like, and thereby, perhaps, like is a more optimal trade-off, like of the assignments of clusters. So putting it all together, so from the central side, so line 2 is where we kind of like create the clusters, the areas. And then from line 6 to 9 is where kind of like we assign, as well as we keep reassigning, like the clusters and into the robots. From the agent side, so it kind of like receives, like its assigned cluster. And then it will then come up with a with the schedule of visits, to kind of like restore its assigned cluster. And then in lines 9 to 12, this is more like of a communication with the central agent, like in cases where, it becomes unavailable, perhaps, let's say it's going out to charge, prompting, like reassignment. So we did some preliminary experiment over a dozen of areas in a structure, in an environment, in an office-like environment. So we tried to run optimal baselines for 1 robot and 2 robots. So unfortunately, running 2 robots is no longer within feasible runtime. So we were only able to run 1. Anyway, in any case, we're using it as like the minimum baseline for any multiple agent. The state of the art actually is effective, which is the orienteering problem, multiple robots with time varying rewards. It's actually effective, in restoring the areas. And we observe that, by increasing the forecast, here it's K. So in other words, the number of schedules for the schedule, it may improve performance. But in any case, our proposed framework outperforms, like this state of the art. Future direction of course, like we want to kind of incorporate in our long-term goal is to incorporate human priorities. As we know, like this restoration task is primarily beneficial or benefiting us. So there has to be like human priorities, as well as allowing agents to collaborate in the restoration task. So of course there will be like continual learning. So robots will infer the temporal phenomena, relying on collected data. So this raises like the trade-off of exploration and exploitation. So that's something we will incorporate in our algorithm. Also, like depending on the attributes of end users, so we will explore like a range like of attributes on how to cluster them, as well as assign. And then also explore best conditions for reassignment, as we just mentioned earlier, and as well as other task allocation mechanisms. So for instance, decentralized approach. So overall, this will enable cooperative multi-agent systems and decision-making, as well as incorporating human preferences, human priorities. That's all. Thank you.
So that we have pretty much the coffee break, and we are like just 4 minutes late, so we recover a little bit of timing. And so the idea is that then I think that hopefully we can get back here like at 11:25, so we can start then with the